can figure out right away how many pieces there are. Just see whether things can be connected. Well, that's obviously connected. Now that has, there are other features of cohesiveness, but this will suffice to show the contrast, because if instead I take the irreflexive value, not necessarily reflexive, then this is the pre-sheaves on a category that has no compositions in it. It's got two objects and two arrows, but they're parallel, so there's no non-trivial compositions to be done. I mean, this looks like a graph, but it's also a category automatically because of the trivial way things connect up. So now, first of all, an object. Previously, we could say that an object was one set, among whose points are the fixed points. So that's the second set. You see, so there are really two sets there, but one is sort of. In this case, we have to say that it's two sets. So an object X consists of two sets, X1 and X0, and again, two arrows that we could call source and target. So the picture of a graph, now here the picturing gets tricky because the conventions for the picture are different. Here, a dot is an arrow, namely a degenerate arrow. Here there are no degenerate arrows. They're just dots, which is a separate thing. A loop, of course, is an element of X1 that goes to the same place under these two arrows. So some dots have loops, but some dots have no loops. In any case, there's no designated loop. Here there's a designated loop given by the canonical degeneracy. So when we talk about morphisms, of course, as always are natural transformations. Morphism in this category is a pair of maps of an S that make two commutative squares like that. And here a morphism can degenerate things. It can collapse an arrow to a trivial, to a degenerate loop, i.e. to a dot. Here you could degenerate an arrow to a loop. If there was a loop to degenerate it to, there might not be any. Or I might not have any loops at all as an extreme case. In which case all these maps will be monomorphisms, by the way. Only things that can map to the anti-reflexive graphs are subgraphs of it. you get a push. Something I hadn't realized until yesterday. Anyway, all right. So what is the point? Since you don't have the reflexivity as a structure, therefore morphisms need not. There is no designated loop. If you tried to designate a loop, it wouldn't help because it might not be preserved by morphism. You have to change categories. I have great problems reading books on graph theory, books and papers on graph theory, because they never tell you exactly what they're talking about. Sometimes the graphs are universal, sometimes they're reflexive, sometimes they're not. So even though they go so far as to talk about homomorphisms, I still don't know exactly what it is, which category are we in. What they should do is admit that they're working in 3 or 4 different categories, and they know how to pass from one to the other, and so on. They'll simplify it. But no, they prefer to talk in a vague way. They're smushing these together. And they've actually tried to understand some of the problems of graph theorists, and I get blocked on the first page if I like that. Anybody actually know what a graph minor is? Graph minor. Big problem. I mean, the guy who's the head of the International Mathematical Union, who's also a big shot with Bill Gates, he promotes this problem. He's famous for working on this problem, on graph minor. And it looks like it might be interesting. But I can't determine exactly what it is, because if you read the first parts of the paper, they waffle, you see. And they don't give you a property. They say, well, you could remove this kind of an edge and put back in that kind of an edge, and a finite number of sequence of steps of that sort would give you the kind of thing we have in mind. But you don't know what kind of thing we have in mind. Now, of course, such a calculational test would be a great thing for a concept that was clear. But it's very hard to have a clear concept that is only that as a so-called definition. You see my problem? Anyway, the basic point is that there are at least 3 or 4 kinds of things called graphs, really 3 or 4 different toposes that are all closely related. They have apparently slightly different properties, but what I'm emphasizing here is that they have radically different properties, because this one is a cohesive and not variable set. Because let's take, now here again you have the generic figure, but actually you need 2. You see, there's just a bare dot is one figure shape, and an arrow is the other. And this arrow means, though, something different than it meant here, because this thing has really only one arrow and 2 dots. Okay? Whereas the basic figure for the reflexive case, it has 3 arrows. It's just the 2 of them are degenerate. So it behaves very different. What if I take the Cartesian product of this one itself? It still has, and by itself, it still just has one component. One component. Again, it's obvious whether the thing is connected or not just by looking. Well, okay. This is, I said, what did I say? This has 2 dots, and therefore the product has 4 dots, just as before. But how many arrows? An arrow is an ordered pair of arrows. There's only 1 arrow in each. So there's only 1 arrow in the answer. And of course it's this one. Pasta. That's the whole product. Which clearly has 3 components. That 1 times 1, not equal to 3. And therefore that action is not satisfied. Now that's a very, very important axiom. Well, as we'll see later, for various reasons why it's very important, but this shows clearly. Now the other thing was, as I was trying to explain in words without pictures before, is that not only do we have this abstract property, which is different, but this one concretely can be seen as a variable set, because, shall I call this A again? Ensure confusion. Well, let me say, there's this general thing that if you look at presheaves on any category C, and suppose X is a particular presheaf, then the slice category, I mean the one which consists of all figures at X of arbitrary shape, that's actually itself again a presheaf category. Namely, the exponent is figures of shape C only, of shapes in C. So that's a basic formula in thinking about these things. So, in this case, what I want to do, I want to say that this is locally a poset. So, if I take the category of non-irreducible graphs, slice it again by the generic figure, the arrow. This is actually just presheaves on this category. And if you figure out what it is, you have to calculate all the commutative triangles and so forth and so on, and see that what it really reduces to is this poset. That's the whole thing. After having sliced, even though double arrow is not a poset, this is a poset. This is a poset. That's actually characteristic of the small category C consists of epics, like in Johnston's QD adequately separable things. If you slice, now in general you can take the sum of all the objects in C, that's a single object in the topos, and slice by that, you get a poset. So that's really the idea of these everything being epimorphic, and that you sort of look at the category of figures, the definition of epimorphism, which says that 2 maps are equal provided you compose them on one side in the right way first. But when you pass to this category of incidence relations, that's already saying any map there is composed with something. So therefore the maps are actually unique. So what?
I think you have to take the like at least once.
You mean I have to talk to it or fight it? What? So this is what you get, okay? Now, this is the picture of the open sets. Did I do that right? No, I get it wrong. It's backwards. This poset can be realized concretely, as I said, this way, that you have a three-point space. I suggested even that you could think of it this way, that you collapse this whole open set to one of them, this whole open set to the other one. It sort of explains why this space, trivial though it looks, is going to come up a lot, because you have to make decisions. Is it greater, equal, or less? Of course, even that's not the only interpretation, but this is one frequent interpretation of this set. So now the thing is that I want, these 2 points are open. There are 5 open sets altogether, because there's the whole thing, there's the union of the two, as well as each one, and the empty set, that makes 5. But really, it's all determined by 2 open sets, with the axiom that says they are disjoint. I think of it as a presentation of a distributed lattice. 2 generators with the one axiom that their intersection is empty, and it has these 5 elements. And this other point, which is not open, but it does mean that the whole space is different from the union of the two. So this is the top element. This stands for the whole space. This stands for one of the open points. This stands for the other open point. And these are the inclusions. So the 2 open points are included in it. So a sheaf on this space, what's a sheaf? Well, in principle, it's a set assigned to every one of the 5 open sets, together with restriction maps. But on the other hand, there's a pasting condition, which means really I only had to know the sets assigned to those 2. And that's without any condition. So it's an arbitrary pre-sheaf on this diagram. Well, for my conclusion, I wouldn't need it to be arbitrary, but it happens to be. So in other words, basically the graph is a variable set along this poset, except that we require that these 2 sets be the same, namely that the arrows are not the same. So it's a kind of a quotient, you see, of something which is an ordinary topological space, namely this one. We take but we think of this as a topos instead of as a space, and so we take the quotient in the larger world of toposes, just merging those 2 open sets without merging the inclusion maps, and get something which is no longer a poset. And that's why it's in a very strong sense, a variable set, because not only does the site not have any idempotence, every map is bound both epi and mono, so we have the intersection of the 2 and the union. Actually, I think there are 5 things there. No. But the non-typical intersection is the one. Does that help?
Since I have a meeting about processes and things.
Oh, yeah. Yeah.
Is that the case that somehow any motion has to be synchronized, you see that?
Something like that.
Whereas the other one, the motion is one of the people can move and the other one. But I have a question still. If there's a duration involved, the degenerate has a duration, even though they have a duration in the product.
Well, okay, so by duration, okay, let's just say when you talk about duration, you're thinking of this as a special case of labeling, right? In other words, in general, given a topos of an object, you can take the slice topos. Right?
See.
So if you have a graph topos, you can take a particular object and slice by it. And so that this amounts to considered labeled graphs. The arrows and dots are labeled. Typically one takes things that have only loops, so you label the arrows or don't worry about the dots. If you take a general label domain, you label the dots as well, but you insist that it's done in a consistent manner. Now all that is true no matter which propulsive graphs you're talking about. Now what you're saying is more precisely, if you think of this duration labeling as having something to do with processes, the kind of processes that can be described as, subtle conditions depend on which topos you're in. I would accept that.
But does that got anything to do with this distinction? How does it affect this distinction? Anyway.
Well, I think, well, you're saying somehow if you want to label time with an irreflexive graph, it's sort of insisting that you go on, you can't stop, or at least a single label you can ensure that you can't stop. Whereas in the reflexive case, there would always be the option of stopping, no matter how you label it. Something like that. What I just said may not be right, but something very like it is true.
What's that got to do with the general question
of cohesive version? Yeah, I don't know. I mean, good. Good. You passed. You asked me a question. What?
Good what?
I said a good question.
Yes.
You go and look for it. Now that it has been pointed out that among all the graph topos, as you can imagine, some are cohesive and some aren't. What does that have to do with the details of how processes can be labeled in various, labeled in various? Is there a clear distinction between the types of process that you can see just from knowing that this is a cohesive version of graph theory or the other kind?
But actually, I didn't even show everything. I mean, is it correct to think that things in both processes are processing, or one should be processing, not the other? Does that have an effect on that question?
Well, look.
Anyway.
Probably not.
Probably not.
Because, why do I say not in general? Because the usual procedure is to work in abstract sets, and then you have a set of states and a set of operators, and in other words, no constrictions at all on how that the actions be morphisms or something. So you can always revert to that case and model anything in some sense. Which is what I wanted to say about the amazing power of sets. Amazing power of sets. They're lost in faith. So basically there's two parts. There is Grossman's, look at it this way. Grossman's book starts with the amazingly clear philosophy, which everyone says is obscure, about how mathematics is divided into four parts. Bigger? Closer to the microphone. And the way you get these four parts is by the interaction of two different contradictions. One is continuous versus discrete, and the other is different versus equal. And my point is that we have a rather precise and also surprisingly rather adequate model for those four aspects here. So essentially we approach this whole question of cohesion in a relative sense. That is, what we want to describe as the contrast between cohesive and not cohesive, E and U, which we could call continuous and cohesive and non-cohesive is really continuous and discrete in some sense. Now there's a big problem what discrete you would think. It's a problem of axiomatizing set theory, you could say, at one end. How can you describe a topos where the things really, really, really don't move? They really, really, really don't have any cohesion. Cantor had this idea already in 1860 or something. And he was sure that if you could do that, then you would have the continuum hypothesis. I think he's right, actually. The continuum hypothesis is true. What does it say? It says if the sets are sufficiently inert, then there's no cardinals between X and 2X relative to. I mean, they don't form any coordinates as cardinals. I think that implication is true. The problem is to express the hypothesis in a sufficiently usable way. And the reason I think it's true is that I think Gödel proved it, you see, except his proof is it's based on induction. I don't like induction. Or to put it another way, the fact that the sets are inert doesn't have anything to do with building them up in an empty set. Using the most narrow possible, definition of constructiveness and all that. It's a different concept, but it is a way of getting at a version of it. But probably, surely the absolutely inert sets is a bit more general than constructible sets. But of course not as general as the sort of thing that's allowed by CF. The whole struggle around, whether the axioms of ZF are sufficient or not is really not the issue. The issue is whether they describe, this inertness. And what happens is, of course, that you can. I don't have a full, obviously, knowledge of all the kinds of models of set theory constructed in the last 40 years. But certainly most of them answer to the following type of description, that you actually start with a system which is a little bit variable or a little bit cohesive. And then you freeze the variation. You look at it with finitary glasses, and it looks like it's not moving, it's not cohesive. In other words, it satisfies ZF. But that's because you're just looking at it using only finitary logic. But the actual concrete way that you construct these models is you do look at things that are genuinely variable, and then you collapse them a lot, but you only collapse them, say, modulo a finitary alpha filter instead of modulo, more complete filter. And that's why they still satisfy those particular axioms, but refute they're not really, really, really constant, and so they don't satisfy people. Anyway, but that's not even the most interesting thing. The most interesting thing is that really the idea of a dialectical contrast between continuous and discrete comes up in other ways, in the sense that what you'd like to call discrete is only relatively discrete anyway. It might have some interesting structure and still be qualitatively opposite to some E that's sitting over it. I've used the word U here because Grothendieck talks about U-toposes, U-toposes. U-toposes in the sense of Grothendieck are just toposes that are defined over U, where U happens to be a model set theory. It satisfies a lot of further properties. But the idea of U-topos could be any other topos. Now, you might like it if it were Boolean, and if it wasn't. But and so forth. I mean, there are all sorts of reasons. As I say in algebraic number theory and the like, it's very appropriate to look at bar atomic sheaves on the category of finite field extensions, which happens to be a Boolean topos. If the ground field is the rationals, it should be called the Galois topos. That's the natural base, not abstract set theory. That's the natural base for algebraic geometry. But there's no reason why none of the axioms that I have force you to be Boolean or anything special. It's just some topos as a starting point, and we have a qualitative need to more cohesive or more variable in the E. So we want to describe what kind of a contrast that is. I'm just talking about the P now. And so in the general discussion, I'll discuss shortly how we can describe models of this, but the kind of thing it should be is, first of all, the geometric morphism of toposes. So it's a function that has a left adjoint, and the left adjoint preserves products. No, left adjoint preserves everything. That in turn has a left adjoint that's called pieces. And so I mentioned three functors. P lower star, which extracts the points, and P upper star, which includes the discrete as a special case of the continuous. You always have this idea that 0 is a number, right? So that among the continuous and variable, discrete and the cohesive and variable, there are those which are not the zeroth case, but the zeroth case is arbitrarily set at U. So P lower shriek extracts from the discrete space of pieces from any given cohesive space. P lower shriek, the left adjoint, as my example before with the components in England and all that. P lower star just extracts the points. So P lower star and P lower shriek are respectively the right and left adjoints of the inclusion of the discrete part. So I've tried to concoct a notation here. I mean, pi 0 is a very, very common notation for the set of components of something. It seems appropriate to try to work inside E as much as possible. So I transport U into E, but then there are two ways to do that. So I have these idempotent functors, pi 0, pi lower 0, and pi upper 0 and the other way, which is simply the pieces and the points, but it's construed again as special spaces rather than in the other category, back in the same category. So there's a canonical map. There's always a canonical map if you have a full inclusion that has both adjoints. There's always a map automatically from the right adjoint to the left adjoint. It goes through the general object. You include the points into the space, and then you collapse the space to its components. And that composite is a map which lives in U, if you like. But it lives in E, but it even lives in U. And that you can think of as placing the points into the piece that they belong. So this is a canonical map that places each point in the piece. Now when I talk about points, of course, that's not a set. There are maps from 1, which you can say those are the Lawvere points, but in general, it's somehow the objective points consists of more than just Lawvere points. And one of my axioms now, special axioms for cohesion, beyond the I should first say P lower shriek should preserve finite products. The typical situation is it's defined as a left adjoint, so it automatically preserves whatever colimits you have, but in general there'd be no reason for it to preserve the limits. But no, we insist that it should preserve products, finite products, not to preserve equalizers and pullbacks. Otherwise, most of the structure would disappear. Maybe, might in some case also preserve, but certainly in the general theory about combinatorial topology. Taking the components certainly doesn't preserve the equalizer. Imagine, I can write it here. Right? In other words, here's F and G. X, pi 0 of X is 1. I.e., it's connected. If I take the equalizer, so I have two maps from X to Y. I take the equalizer, well, in my picture it's just these 2 points. So if I apply the functor pi 0 to this diagram, it's no longer an equalizer diagram. Because actually both of these are 1, I should say, to make it clear. Both X and Y are connected. So the equalizer is not connected. So pi 0 doesn't preserve equalizer. And by the way, this is typically how you construct non-connected spaces, right? The real line is connected, complex numbers is connected, but by solving equations, you produce objects of, non-trivial combinatorial form. But it should preserve products. Should preserve products. So that's one of the axioms, besides the existence of these adjoints. Another one is the nullstellensatz. Now, what do I mean by the nullstellensatz? Nicoletta was complaining the other day about how in school they teach you to take the equation of a line, put everything on one side and 0 on the other side, not knowing why you do that. Of course, the reason why you do that historically is the fact that you work in rings that have subtraction, and so you can translate any equation into an equation saying that some other thing equals 0. And this is sometimes very useful. Of course, everybody knows it has the great usefulness that if you can factor that thing, then you can tell a lot about the roots using the factoring. But except for that, it's a bad thing, because this whole business of subtraction, 0, and so forth, has really, in general, nothing to do with the issue that two things could be equal. So Anyway, I'm just explaining the term nullstellensatz. Nullstellensatz doesn't really have anything to do with null, except tradition, because of that way that you described formally in the idea that two things are equal, by saying their difference is null. So you could ask, given variable quantities, are there any points where this happens, that two things are equal? But that's a null point for their difference. So going through this whole translation, you come up with this idea of a statement that there exists 0, but it really just means points where two things are equal. Anyway, so the null, and then of course the way that's applied in algebraic geometry, you have some equations. First you take the space where the equations are true. And if the system of equations was, quote, consistent, unquote, it means you have at least a non-zero object of your category, but it may not have any points. So the nullstellensatz says that it has points. Well, again, points are maps from something that's coming from below. So if below is not algebraically closed, you need this other Galois topos, not abstract sets, in order to talk about it. With the points, in other words, are going to be defined over extension fields that's possible. You still say they exist. The original formulation of Hilbert was assuming algebraic closure, of course, in which the points are just maps from 1, and you just have abstract sets below. But it's easy to see that implies, for an arbitrary base field, the existence of points defined over some infinite extension. And that's exactly what it's the kind of thing that this is requiring. So, So my actual statement, I haven't said it yet. It's just a statement that this canonical map is epic. This map is epic. So intuitively, it's saying points exist. More exactly, it's saying that in every component, in every piece even, not just that the space has points, but every piece of the space has points, where has is the existence in the internal logic of the topos and so on. So every piece has points, existence of points. Now, that's that axiom. It's possible that an analog of my theory would go through without this. This is certainly important for many of the constructions. Shall I say? Well, yeah. Well, okay. Of course, when I talk about equal and different, it's easy to substitute all sorts of stuff under that. I mean to give it a rather concrete meaning, but let's just say that this raises the question, okay, that map is epic. Could it be an isomorphism? Could it be an isomorphism? Could they be equal? Could for a given space, the subspace of points and the quotient space of pieces actually be isomorphic? We have the canonical map. We said that it's epic. So we're saying could it also be monic, rather than topos monic. Well, let's think of the example. I told you it was a good example. Reflexive directed graphs. Just think about it. If you have a reflexive directed graph, what would it mean for the map from points to pieces to be a bijective? Well, we would say that every piece has one point. You know what a piece is in the graph. So it's saying that the graph has only loops. Any graph that consists entirely of loops, if and only if. A graph will have this map isomorphic, if and only if it consists entirely of loops. It can have at any number of points. At each point, it can have any number of loops. But that will... Now, in another paper, I don't know if it's... Yeah, that's right. In fact, I should have said I have published a paper actually. I mean, sometimes I do that. There's something called TAC, T-A-C, Theory and Application of Categories. It's a wonderful electronic journal run by Bob Roseberg. And I actually published something in there last year called Axiomatic Cohesion. So there I give another slightly different example, namely reversible reflexive graphs. Reversible reflexive graph means that for every arrow, there's another mate which goes backwards. So there's an operation which to every arrow assigns a reverse, as well as Now it turns out that complicated description is nothing else but just an arbitrary right action of the four-element monoid of all endomaps of the two-element set. Everybody knows what a two-element set is. Everybody knows that it has four endomaps. Two are constant and one is the inclusion. So any right action of that is a reversible reflexive graph. Now there is what some people would throw away as a complication they didn't want, but of course that's precisely the sort of thing that encodes all the information in the universe if you want it to. That there are loops which have the reverse. There are also loops which are their own reverse. That's the possibility you might not have thought of first in that description. Every arrow has a loop, and you have loops, of course, but some loops, not all, some, are their own reverse. Actually, if you think in terms of geometric realization by intervals and so forth, it's natural to think of those as sort of, instead of as loops, as they go out and then they come back along the same line. Of course, there are no actual lines, but to picture it, how you do apply the geometric visualization. That's the sort of thing that you would get. You go out up to time equal 1/2, and you go back along exactly the same route. T and 1 minus T goes from 0 to 1, over up 0 to 1/2. So in other words, there are two kinds of loops. So if you do the same thing, you ask which reversible graphs have the property this map is an isomorphism, then you see that it's much more complicated because it's a bunch of dots and then there are loops, but then some of the loops are reversible. So they're reversible, self-reverse. The self-reverse and the others. So the idea is you should think of those as things like atomic numbers. So at each point, one of these apparently stupid objects where this map is an isomorphism, actually at each point you have information of the sort atomic numbers, quantum numbers, or whatever the generic figures are, possible interpretation. So there's a lot of information. So now, you see, by doing that, what I've done, I take the solution of this equation, which is, at first glance, it's a subcategory V, of course. But that subcategory is really the inverse image, just like this was. This U is a subcategory of V. So this is also a subcategory, with both left and right adjoints. S lower shriek and S lower star, calling this thing S. So, obviously, given any graph at all, either reversible or not, it always reflects it, whichever topos you want to be in. Given any one, you can simply take those loops and throw away the interactions. Well, that's the right adjoint. That describes the right adjoint, the S lower star. Instead of taking points, which we're doing at the lower level, we're doing something more informative, more sophisticated. We're throwing away the interactions between different things, but we're not throwing away the self-interactions. So it's just like the points, except at this higher level. On the other hand, the S lower street means you take the graph, and then you take the components, but you don't just take names for the components. In fact, you keep all the arrows, too. Keep all the arrows, except you identify all the dots that are in each component. So in each component, you identify the dots. You get a huge number of loops. Now, everything becomes, every previous arrow becomes a loop. So you forced every arrow to be. Now, I call this, in order to sort of imagine this, I think of a piece of matter, might be some H2O. If I superheat it, see, so that the particles are so far apart that the interactions no longer matter, that's lower star. I think of that as the Avogadro version. We talk, it's the substance, right? The fact that it's H2O is a property of the dot, it's a property of the atomic numbers or whatever it is exactly, the molecular structure at each dot. It doesn't matter whether it's heated up like that. That my little sample of water is dispersed throughout the whole solar system or whatever. It's still H2O. But it's essentially one of these dots, one of these things where every connection is a loop. On the other hand, if I freeze it and then I superheat it, superfreeze it, push it way down, I get supermolecules. So this is the Bose version. You get the supermolecules by merging the atoms, but not losing all the interactions became now self-interactions. That's S lower street. And there's a natural map again, because we have a full inclusion of two adjoints. As always, we have a natural map, which I call cooling. In other words, if you do these two experiments, superheating and supercooling, but there's also a partial relation between them. for, Van der Waals describes what happens when you cool something, it passes through a changing state. But anyway, that's not quite what happens here, but certainly there's more information, in fact, that in this supermolecule, some of those loops were already loops before, whereas others were not. You see, so that distinction you would not know from just the two objects that it's specified by the canonic map. So this construction is fundamental to the type of analysis. Now, I want to think of these L's also as infinitesimal. In other words, there are many features that infinitesimal objects have, and especially in differential geometry, they have still more special ones. But to some extent, let's say I'm investigating hypothetically, what will occur if I just assume that infinitesimal means object in this subcategory L. So in other words, the graphs that consist only of loops, those are the infinitesimal graphs, and so on. So it will turn out that there are many properties that you can expect of infinitesimals, and this is a useful way, maybe. But maybe it's too general, but it's useful because it's pretty restrictive anyway. So I think of this as, here comes another. I don't think Grossman showed how to do this. Maybe he did. He did a lot in 2 pages. But to derive the notion of quality from this setup, continuous versus discrete, different versus equal. I want to call this Q here. This Q is, again, essential geometric morphism, but it has this property that Q lower star equals Q lower 3 by construction. I just took those objects for which it was true. And then P is equal to QS. Q is just P except restricted to those objects. But for them, the two sides are the same. So I want to call that a quality type. Why the hell I want to? Well, you see, because S is a quality. S is a quality which is valued in the type Q. And the quality is substance. This sample, what did it consist of? H2O. Well, that's the substance of it. So, in fact, you see, wait a minute, let me as well write this sum somewhere. Write this down somewhere. So Q, the two adjoints are the same for Q, so it's a quality type. It's like K-theory. The idea is if you want to measure the objects in a category, you have to first figure out where the measurement is going to take its values, because they probably won't be simply natural numbers or something. What that is will depend on the category. So the measured quality will first have to be specified as another category of this special type relative to U, and then the actual process of measuring also. So the point is that the quality, right, the S Q lower star is the same as Q lower shriek, but I want to write it that way because I want to say that this is S P lower star. So in other words, that the functor that measures the quality preserves the points aspect. Doesn't preserve the pieces aspect at all, because the thing is still made out of the same substance no matter how many pieces there are, etc. So it's a functor I'm talking about mapping. P is really a string of adjoints, so is Q a string of adjoints, but Q is a collapsed string. So if I'm considering mapping, and I'm not just mapping one category to another, I'm doing it in a way that's somehow related to these strings of adjoints. But the special property is that this one is compatible with the points. If I extract the graph, part of the graph, it's just only in loops. It still has the same points as the original graph. I preserve the points. So I call that intensive quality. By the way, Grossman, you see Grossman correlated things being equal with intensivity. So quality in general refers to mapping to something where the adjoint string is collapsed. Intensive quality refers to doing that in such a way that preserves the points aspect. So because there's the opposite, difference, it correlates with extensive. So there are also extensive qualities. And in fact, the left, this is really S lower star. That's what I wanted to say. S lower shriek, the Bose construction in that picture, is an extensive quality because it's compatible with component, with pieces. Rather than with points. So mapping an adjoint string to a collapsed adjoint string, these are two special cases. One where it actually preserves the leftmost adjoint, and the other where it preserves the right adjoint to points. Now, okay, this philosophical idea of equality and difference, I think what we've done here, the idea of equality has been sort of refined to nearly equal. Inside, by the way, when I say these spaces are infinitesimal, I mean their components they're big, but they're made out of infinitesimal stuff. With no connection. It isn't that they are as spaces. I mean, they're made up of tiny pieces. But I found it more convenient, just to, if you like, it's a matter of convenience, consider sums of infinitesimals and call it infinitesimals. Should have said that before. But so it's about being very nearly. You see, Euler says an infinitesimal is zero, and yet it's not zero. Okay, so it's equal to that point, but it's not equal either because the little cloud around it doesn't consist only. So these things that people say are nonsense in Euler, you already see it's very profound. You're at the point, and yet you're not at the point. Depends on whether you take the underlying you, or you take the L itself. So nearly equal. It's somehow connected with things being nearly equal. With equal within that is a special case. But it's not different. You can't say that it's different because there's only one point there. So I think of this as kind of, between Heraclitus and Cratylus. Heraclitus says you can't step in the same river twice. And then Cratylus, in order to provide fodder for his son, his pupil Plato. He said, well, you can't even do it once. And of course, he's wrong. You can do it once, but while you're doing it, you're also doing something else. Or the river is doing something else, moving. So the fact that when if you think of a map from one of these infinitesimal objects to X, and say it's one with just one point, then this is stepping in, that X be the river, and you're stepping into the river. Well, you are doing it at one point, because there's only one point that you get as a composite. And yet, the map itself is certainly more than that point. It's just telling you where the whole thing goes. But you wouldn't want to say that X is different from that point, because there's no other point for it to be at in the time parameter. Okay, so I think this is the best solution to the Heraclitus idea. That this canonical map is an isomorphism. So these are the germs of motion, etc., etc. All right.
If you want to make a break at some time, but it's sort of
make a break. Yeah. Okay. No, well,
it's not necessary.
I know. No, let me see what we're going to do. What do we do about that? Yes. Let me just say, okay. I told you 2 axioms. There's a third axiom. Just so you'll have it down all at once. These are topos, which again, topos really means comparison of 2 topos. So one is, bonus not only exists, but preserves products. And another one was that going from points to, I put it in terms of the phi's or the p's, it's just a matter of, but that's epic, that's the Nullstellensatz. And the third one that I didn't mention at all yet is that for every object, there exists another object, the monomorphism, with the property that phi 0 or p lower sheet is 1. In other words, every object can be embedded into a connected object. And that's clearly true for both kinds of graphs. You see, if you have any graph, well, you have some dots that aren't connected. You'll put some in. Just put some in, and you've got many ways to make it connected. But from that example, it seems like something almost trivial. But if you think instead of G sets for G a group, you can't for G sets for G a group, there's only a finite number of connected things anyway. Namely, they correspond to stabilizer subgroups, which is subgroups of the group, so small in number, even though the category is big. So you couldn't possibly embed every G set in an orbit with the same G. So the character of it is totally different. You can't looking at the graphs, and it could be misleading in that way. It's a non-trivial property. It's trivial for them. It seems trivial for them. Now this can be put in various ways. It's equivalent in various things. But for one thing, you could take x tilde to be the particular functor which started me off on this whole thing of axiomatizing the topos and finite number of axioms. Then you just do partial map classifier. Partial map classifier is a specific monad on any topos which classifies partial maps. It sort of looks like this. You see, you have the object, but then you add to it some stuff. Well, down here is false. And from each point here, there's a copy of the truth value object. So whatever this was like, this result is connected. In fact, it's contracted, and it's connected at least because you can sort of, by just multiplying by truth values, you can decrease the domain of definition until it's not defined at all. So you tune the thing out of existence just by multiplying by a given truth value, by various truth values. You tune a given map is defined, a partial map is defined somewhere, you tune it to where. Now the tuning, this will make the whole thing connected if pi 0 of omega itself is connected. I mean, intuitively, right? If these lines are connected, then I made the whole thing connected because I can always go down and back. Well, that picture is slightly crude, but it's correct nonetheless. In fact, for the truth value to be connected is the same thing as this whole thing here. There exists some connected container of a very general existence, but that implies that omega itself is connected, and if omega is connected, in any case you always have this partial map classifier monad, and that will be connected as well. So you can have a functorial. So the intuitive, I always think of it like this, that X might itself have been a disjoint union. In other words, you might have thought that the people on Mars and us are totally disconnected, but then you can make a bigger space which involves more advanced technology, and now we're connected. Something like that. Things that you thought weren't connected, actually, if you change the object, they are. But you can't do that with T-sets. It's not. When you say it that way, it just sounds like one of those arbitrary things you can push around. No, depending on the nature of the category, you usually can't do it. Typically can't do it. For cohesive toposes, you can. So those are the three axioms.